In Chapter 2, we said this is what acceleration is. Acceleration is a change in velocity with respect to time. That's what it is. Acceleration is change. It's change how you move. Now we're saying how you get it, how you produce it. And we're saying now you produce an acceleration by pushing on something, by applying some net force. But how much acceleration depends upon the amount of matter. This idea is Newton's second law of motion.
Let's pick up this idea in this screencast. We'll apply Newton's second law and resolve the mystery of Galileo's Leaning Tower of Pisa experiment. Back then, people believed that falling speeds depended on weight. A boulder 10 times as heavy as another should fall 10 times as fast. But Galileo showed otherwise. Objects of different weights fell to the ground in practically the same time. But Galileo had no convincing explanation, which we now see is given by Newton's second law, which connects the concepts of acceleration, force, and mass. A boulder 10 times as heavy as another has 10 times the gravitational force acting on it. Is the force of gravity really greater? You'd know it to be so if it dropped on your foot. So why doesn't the heavy boulder fall faster? Because the 10 times as heavy boulder has 10 times as much mass. That's 10 times as much resistance to a change in motion. Newton's second law shows that the ratio of force to mass is the same for both falling bodies. So both undergo the same acceleration, and when acceleration is due to gravity, we call it g. We neglect air resistance, quite small compared to the weights of the boulders. Why Galileo couldn't explain the constant acceleration of free fall is historically fascinating, for it was Galileo who both introduced the concept of inertia and defined acceleration. But he didn't connect these two concepts with force. This connection of acceleration, mass, and force was made by Isaac Newton, Newton's second law, the primary law that first got us to the moon. We say net force here to include times when more than one force acts on an object. When the net force is only weight, mg, look what Newton's law tells us, that whatever the mass, the acceleration is g. Let's apply this to rockets. When you see videos of a rocket lifting off its launching pad, have you noticed that the acceleration begins very small? But soon after, its acceleration increases dramatically, even while the propelling force stays constant. I leave you with a question. Constant force, increasing acceleration, hc. How come? How does a rocket increase in acceleration while force stays constant? Let the equation guide your thinking. Until next time, good energy.